This is a lecture on an op-amp circuit called a voltage follower, and also we'll talk about the use of a voltage follower, which is that of preventing what's called loading. So first of all, here's the op-amp configured as a voltage follower, and notice that there's a short between the inverting input and the output. Okay, and then we have our input signal that comes into the non-inverting input. So if you were to look at the non-inverting amplifier that we did last time, and then just imagine that we remove this resistor RA. Okay, so we put an open where RA is, so this is no longer there, and then we replace RB with a short. Well, if you were to make those two changes to a non-inverting amplifier, you would end up with this voltage follower. So a voltage follower is a type of non-inverting amplifier. So one way to come up with the closed loop gain for a voltage follower is to look at the non-inverting amplifier closed loop gain that we came up with last time and replace RA, which is the resistor that connects from the inverting input to ground, replace that with an open or infinite ohms since it's no longer there, and replace RB's value in the equation with 0 ohms since we put a short in the feedback. So V out over V in for a voltage follower, it would just be infinity plus 0 over infinity, which is just infinity over infinity, which is just equal to 1. So you see, for a voltage follower, V out is just going to equal V in. Okay, and you may say, well, what good is that? Why would you even use this if all you're getting out is what you're putting in? Like, why even have it? Well, I'll get to that in just a little bit, but before I do, I just want to show another way that you can come up with the same answer, that V out equals V in, without plugging into an equation. And that other way is just understanding that, as we talked about before, part of a virtual short is that the voltage between the two inputs of the op-amp is equal to 0. That's the VI that we've talked about. So again, when you have 0 volts across something, it means that on both ends of that something is the same voltage. So since there's 0 volts across these two inputs, whatever voltage I have on the non-inverting input, I'll have the same voltage on the inverting input. And on my non-inverting input, I'm feeding in directly V in. So you see there's V in also on the inverting input. And then between the inverting input and the output, we have a short. And as you learned in your circuit theory, and as we talked about in this class, there's 0 volts across a short. So that means on both ends of the short, you have the same voltage. So since we have V in on this side of the short, there's also V in on the other side of the short where we have V out. So that's another way to show that V out equals V in for a voltage follower. Now, the big application and the big use of a voltage follower is that it prevents loading. So what I'm going to do next is an example to show what loading is, and then explain how a voltage follower prevents this. So here we have a circuit at the top, which you can see is just a series circuit of a 12 volt source. This is 12 volts, along with a 1K and a 3K ohm resistor in series. And if you were to do voltage division to find the voltage across the 3K, it's just going to be 12 times 3 over 4, right? 3K over 4K. So 9 volts. Okay, so across this 3K we have 9 volts. And say we now want to hook up a device, you know, some device, let's say, well, just we'll leave it just some device D. It could be anything, a radio or you know, some other device that works off DC voltage, that works off 9 volts DC. Well, you may think that if we just connect this device right up to this resistor, that since this device is in parallel, with this 3K resistor, there should also be 9 volts across this device. But you see, what you have to take into account, and this is where loading comes in, is that this device is going to have some sort of internal resistance. And just to make the numbers easy here, let's say that this device had an internal resistance of 3K ohms. Okay, so we're just going to think of this device as a resistance, 3K. Okay, so this is the internal resistance of the device. Alright, well, as you know, when you have resistors in parallel like this, the REQ of those parallel resistors is just going to be product over sum. So here we'd get, let's see, 9 over 6 K, so it'd be 1 1/3 K. So these two 3Ks together now, right, we'd have 9K squared over 6K. So that's going to be 1.5 K. I think I might have said 1 1/3 before, but it's 1.5 K. So now if we do voltage division again for the voltage across the device, okay, which if we find the voltage across the REQ of these two together, across the 1.5 K ohm, well, that would be the voltage across both these 3Ks in parallel, so therefore the voltage across the device. Well, it's going to be 12 times 1.5 over 2.5, and that comes out to a little over 7 volts, okay, 7.2 volts. So you see, when I hook up this device across this resistor where there was 9 volts before I hooked up the device, after I hook up the device, there's going to be less voltage. There's going to be a couple of volts less. And that's because when I connected up the device across that 3K that had the 9 volts across it, well, just by connecting the device up, I'm taking away current that was flowing originally in the circuit. See, before I connected up the device, all the current was flowing through the 3K, the 1K, and this 12 volt source. But now, once I connect up this device, some of the current that was flowing through this 3K is now going to be diverted over through the internal resistance of the device. And that means this current flowing through this 3K is going to be less than what I had before I connected the device up. And when this current decreases, the voltage across that resistance decreases. See, that's why you saw a drop of a couple of volts here. And if you have a device that operates on 9 volts, like a 9 volt radio, well, that device is not going to work now because it doesn't have enough voltage to operate it. So that's what loading is. Loading is when you connect something up to a circuit and it takes current away from that circuit, thereby dropping the voltage at that place in the circuit. And you know, this can be something undesirable in a lot of cases. For example, the case of the radio, because the radio is not going to operate off 7 volts since it was designed to operate off 9 volts. So what you can do to help with this situation, and this is where the voltage follower comes in, is that you can take the same circuit here, okay, the same 12 volt source and 2 resistors, 1K and 3K, and then connect this node that has the 9 volts right up to the non-inverting input of the voltage follower. And as we said earlier, V out over V in, the closed loop gain of the voltage follower is 1. Okay, and you see this is V in here, the voltage follower, right on the non-inverting input. So whatever voltage I have at this non-inverting input, that's what I'm going to have at the output. And you see, the voltage follower prevents loading because it has high input impedance. Okay, so you see voltage followers have very high input impedance, which means it doesn't take any current. Okay, the current and you know, we've seen this before with the op-amp circuits, is that the current at the input of an op-amp, and especially a voltage follower, is ideally zero, and in the practical case it's so close to zero you can it's a good approximation to use the ideal. So that keeps all this current in this circuit, which will keep the 9 volts across the 3K, and that 9 volts becomes your V in. So V out here will be 9 volts because of the closed loop gain of 1. So now if I put my radio or my device, whatever it may be, that operates off 9 volts right at the output of the voltage follower, well, it's going to work fine. So that's how the voltage follower prevents loading, is that with its high input impedance, it doesn't divert any current away from the circuit that you connected up to. And then since it has a closed loop gain of 1, you're just going to get the voltage that you connect to the input at the output, and that's where you can put whatever you are going to connect to the circuit directly. You can then put it at the output of the voltage follower, and everything's going to work just the way it should.